ladies and gentlemen. This is Dr. Zulke, and our lesson for today is how to write electron configurations using noble gas notation. Noble gas notation, my students often like to call shortcut notation. Writing electron configurations is fun because you get to start sounding really smart: 1s2, 2s2, 2p6, 3s2, 3p6. And after a while, we get to these really long ones, and students realize that they all start the same way, and suddenly it's not so fun anymore. And it starts taking up the page. And why do we have to do this? Can't we just write the last sub-level and be done with it? Well, chemists kind of think the same way too. And so that is why they developed noble gas notation. So the noble gases are the elements at the far right-hand side of the periodic table. And they get their name because I call them the snobby elements. They do not want to react with other elements. Oftentimes, for example, we'll store chemicals that are really reactive under argon to keep them reacting with other substances. Xenon can be made to react with fluorine under extreme temperatures and pressures of laboratory conditions, but normally these elements never form compounds. And so where noble gas notation gets its name is, let's start with neon. So the standard electron configuration for neon is 1s2, 2s2, 2p6. So I've got my different blocks labeled. S is red, P is purple, D is green, and then I've got the F block down here outlined in blue. And remember that 57 and 89 are part of the D block. And so 1s2, 2s2, and then 2p, 1, 2, 3, 4, 5, and 6. That brings us to neon. Magnesium's just a little bit bigger, and so it ends with the same beginning, and then it ends in 3s2. So the noble gas notation is really just a substitution. We say, okay, 1s2, 2s2, 2p6 is the electron configuration for neon. Those are core electrons. They're not as much interest to the chemists because they're not taking part in bonding. The 3s2, these two electrons are the valence electrons. Valence means outer, or at least that's the way people interpret that. Valence also means it determines the mood of the atom. So in literature, if you talk about the valence, it's the mood or the ambiance, or my students like to call it the vibe. So it's then neon, and you got to use square brackets. You can't use parentheses. You put the symbol inside. That replaces the electron configuration for neon, and then it's 3s2. And that's all you got to do. Let's take a look at another example. We've got phosphorus, which is also a period 3 element. It's a little bit bigger. You have to put a noble gas in the noble gas notation. Some students want to start with magnesium. You can't just start with the previous sublevel. You've got to include all those valence electrons. So to find your noble gas, you go up a row and over, which gets you to neon again. And then we substitute, so it becomes neon 3s2 3p3. So let's go through some additional practice problems. We'll do the first one together, and then the other ones I'll give you time to stop and pause the video while you work out the problem, and then you can check your answers. So iron, noble gas notation to write iron. So the first part is you're going to spend some time just finding these elements. And so I'm giving you the answers. I didn't mean to do that. Okay, so iron is here. We've got, it ends 4s2, and then remember the D sublevels are one behind because those D sublevels are really long and skinny, and they take the electrons farther away from the nucleus, so they're higher energy. So remember, it's the number and the letter together that determine the energy of the electrons in that sublevel. And so even though 3 is smaller energy than 4, D is higher energy than S, and that D being higher energy is enough to make the 3D sublevel higher energy and fill later than 4S. So we start out, we've got to go up a row, find iron, and we go over. And I know there's no elements directly above it because there is the 3D sublevel is buried down in period 4. We go over and we find argon. And then remember, the elements are numbered. So if you go lost from here, you're at element 18, and y'all know how to count. So let's go down to 19. And that tells us we are down in period 4. So it's 4s1, 4s2. And then it's 3D, 1, 2, 3, 4, 5, and 6, which gets us to our answer, argon 4s2 3d6. So take a look at this next one. This one is rhodium. Rhodium is down in the 4D sublevel. Pause the video here and figure it out, and then we'll check it together. Right, let's check our answers and explain. So rhodium is here, it's number 45. You go up a row all the way over, that brings us to krypton. It's element 36, so krypton is in the periodic table. The next you go down and you get element 37. We are in sublevel 5s, and then we move into 4D, and it's 41, 2, 3, 4, 5, 6, and 7. And I seem to be really good at flashing answers today. Iodine. Iodine is down here. It is down in the 5P. Pause the video and work out your answers. Right. So checking on iodine, we go up a row and over. And make sure you always go up a row because iodine is number 53. If you go straight over to xenon, that's 54. It's like missing your turn because you're starting out substituting and then continuing. If you just go ahead, you can't do that. So if you just go to the right, you're too big and you've missed it. So you start out with 36 electrons, 4s2, 4s3. Now you're with 38 electrons. You've got another 10 electrons in the 4D, and then you get to 5p5 and you're done. All right, uranium is the largest man-made element. It is down here in the F block. And the F block is where electron configurations and the Aufbau diagram diverge. And oftentimes the F block elements, chemists may still be disagreeing on what their correct electron configuration is, or they may be irregular. So at least with my students, typically I give students the electron configuration and ask them to figure out the element. We can talk about how to do that in just a minute. But uranium is down here in the F block. And so remember, if we look at period 7, we've got this is 7s and 7p. We've got this whole row of elements is 6d as well as the actinium. And then we've got this is 5f. So the f orbitals are even longer and skinnier in the d orbitals, and they fill up very, very late. So 5f fills after 7s, and it fills sort of around the same time as 6d. It's a little bit strange. So uranium puts 2 electrons into the 7s. It puts 1 electron into the 6d, which is why I've got this boxed in green as being a d element. And then 1, 2, 3 is uranium. If I were to give you the electron configuration and ask you to figure out what element we have, let's go back. I would say find radon, and radon has got 86 electrons. And so radon is here. It's got 86 electrons, and then we add 2 more that gets you 88. And then this is 89, and then 3 more is 92. So then you go and if you assume that this is a neutral element, then you find uranium, which is element number 92, which leads to my next question. So what is the name and symbol of the element with the following electron configuration? So this is similar. You're going to find radon, which is here, move down, and then we get 7s2, and that gives you radium, which is here. And I believe this is the end. All right, last one on this slide. Xenon 6s2, 4f14, 5d10, 6p3. Pause the tape or the video, and then we'll check it. I bet you can figure this one out on your own. Okay, let's check your answer. So we've got xenon, and then it's 6s2, and then we're going to write 4f14. And one of the things that students get confused about, they're like, don't I need to write 5d1 and then like 5d9, or how do I indicate that it's 5d2 through 10? Remember, electrons are not really collecting in the atom one by one. And the 4F14 and the 5D10 sublevels are really similar in energies, so it doesn't particularly matter which one you write first. Both 4F and 5D are full. Just make sure that you get them in there and don't forget the 4F14. So we've got 4F14, we're filling up all of these guys are full. Then we've got 5D10, which corresponds to this region of the periodic table, and I lost my answer. And then we go 6P1, 2, 3, and that brings us to bismuth, which we know of in Pepto-Bismol. Nobody really likes bismuth, Pepto-Bismol unless you need it. But yeah, bismuth has actually got a little bit of a pinkish tinge to it if you see the element. And so thank you for joining me. This is Chemistry with Dr. Z. And my slides that go with this have additional practice on it as well. Thank you.